This is lecture number 6 on primitive roots and indices. And in this particular video, we'll be talking about primitive roots for primes. We have already seen in my earlier video how to check whether a primitive root exists for a particular modulo or not. I have added the link of previous videos in the description box. In this particular video, I'll be only doing the theorem which ensure the existence of primitive roots for the prime. So let me to write down the statement of the theorem and then we will prove it. So the theorem says if p is a prime number and d divides p minus 1, then there are exactly phi d incongruent integers having order d modulo p. Now of course if p is prime, then we know that p minus 1 is not a prime number. And if p is a prime, the only even prime is 2 and for all other primes are odd. So this means if except in the case when p is 2, for all other cases when p is greater than 2, this is odd, and that means p minus 1 is an even number. So we are considering all the divisor of p minus 1 and we say that there are exactly phi d incongruent integers that have order d. So when we say order d, that means there is an integer a whose order is d, which means it is congruent to 1 modulo p. So that speaks about ensuring that a is the primitive root of p. So that is how it talks about the existence of the primitive root. Now let us see the proof of this theorem and then we will take the example. So now first I am going to prove this theorem using the mobius inversion formula. So I am going to use mobius inversion formula. And before that, let me to recall what is the mobius inversion formula so that we don't have to again and again recall that one. Given two number theoretic functions, which are related with an expression. So let me to take two number theoretic function fn and small fn, and they are related with the expression and related as capital Fn is equal to summation of d divides n. So d is a divisor of n and then we have f of d. Okay. Then using Mobius inversion formula, what I can write this as, I can write small fn in terms of capital Fn. So this means I can have an expression Fn that is same as summation d divides n mu d into capital F of n by d, or I may also write this as, because n by d is also a divisor, so we may write this as d divides n mu of n by d into f of d. Okay, so here inside this bracket it is actually the divisor, whether we write n by d or we write it as d, because n is always written as d into d dash if d is a divisor. So this means I may consider n by d is also another divisor, d dash. Okay, so now I'm going to use this theorem for proving my previous case. Now let's start proving this case. So what I first need to consider is, what is given to me is, let d divides p minus 1. So this is given to us. P is a prime and d divides p minus 1. And let us see xi d. This is a notation that I'm using. This denote the number of integers. This denotes the number of integers k such that k lies between 1 and p minus 1 that have order d modulo p, okay, because each integer between 1 and p minus 1 has order d for some d divides p minus 1, and here we say p minus 1 is equal to summation d divides p minus 1 xi d. Okay, this is what we wanted to consider. Now why this statement that I have written here follows up. We consider xi d denote the number of integers that lie between 1 to p minus 1. So this means if I consider this k, this k runs over 1 to p minus 1 and we have considered the prime as p. So this means all those k whose GCD with p is equal to 1. So this means the selection of a also when we say that A is a primitive root of P. So the selection of A also comes from this set 1 to P minus 1. So that means each number, each A will have some order modulo P. And we are also saying that 1 to P minus 1 have some order D. Order means that for these numbers something is going to A raised to power D must be congruent to 1 modulo P. This will always going to follow up for some D. And when we sum this quantity P minus 1, now why I am going to sum this quantity? On this side, this is my total number P minus 1, and here I'm on the right hand side, I'm summing over the xi d. Xi d is the count of integers which have a particular order. Now two integers will not have a same, two integers if they have the same order, they are going to count it here. So let me to take an example to explain this particular statement. Let's take an example here. Let's take n is equal to P is equal to 13. This means P minus 1 is equal to 12. So this means I want to consider now the divisors of P minus 1. This is what we want to consider. And what are the divisors? That means the possibility of divisor is, this may be, we have a set because D divides 12. So the divisors will be 1, 2, 3, 4, 6 and 12. So these are the possible cases of the divisor. And I wanted to know what is xi d. Xi d denotes the count of integers which lie between 1 to P minus 1 that have order D modulo P. Now what are the order D modulo P? Now let's see again. So in xi d, the choices for A that I'm going to look up for the order also, that will also lie between 1 to 12, the whole set. Okay. If A is equal to 1, then I need to search A to the power D is congruent to 1 modulo P. If D is smallest such power, then this will become the order of A. Okay. Now let's take D is equal to 1. So let's take A is equal to 1 first. So 1 raised to power D is congruent to 1 modulo D. So what is the possible choice for divisor? 1. So here D has to be 1. This means there is only one integer. So let me to write here. There is only one integer. Let's write this as set 1 to 12. So there is only one integer in S which have order 1, and that is 1. So I may say 1 has order 1. So 1 has order 1. Now look at the second case. If A is equal to 2, then let's start increasing the power. 2 to the power 1 is congruent to 2. So we want a situation when it should be modulo 13, because in this case this prime was 13. So 2 to the power 2 would be congruent to 4, 2 to the power 3, that is 8. This is congruent to 8 modulo 13, and keep on moving like this. We will see that it is only 2 to the power 12 that comes out to be congruent to 1. In none other smaller cases it turns out to be congruent to 1. So this means in a similar process, similarly, we will have 2 has order 12. 2 has order 12. Then we will look for A is equal to 3. What is the order of 3? If I look 3 to the power 1, that is congruent to 3. If I look 3 to the power 2, that is 9. 9 is congruent to 9 modulo 13. If I look at 3 to the power 3, 3 to the power 3, that is 27. 27 is congruent to 1 modulo 13. That means 3 has order 3. It is not a primitive root. What we are talking about is the definition of the order. So this means 3 to the power 3. So 3 has order 3. Look for A is equal to 4. And if we start searching, we find that 4 to the power 6 congruent to 1 modulo 13 comes up. So this means I may say 4 has order 6, and we continue this process till when A is equal to 12. So we can see here that 12 has order 2. 12 square, that is 144. 144 is congruent to 1 modulo 13. Now consider them as a divisors form and try to make this list. What we are saying, we want to see that it has in the form of a divisor. Let's try to make now the list according to divisor reading from here. So I'm going to now rewrite this statement, all the orders in the form of the divisor by looking the construction that we have done here. We have considered all A's, but now I may write my list in a consolidated form. 1 has order 1, we have verified just before that. We may say 12 has order 2, which is fine. We may say 3 and 9. These are the two possibilities of A. They have order 3. We may say 5 and 8 has order 4. We may say 4 and 10 has order 6. And 4 numbers, namely the remaining one, 2, 6, 7, 11. These have order 12. These have order 12. So even in this case, so these have order 12. Now this side, this sort of list, it consisted of all A's which belongs to the list 1 to 12. And on this side, if I look at this side, this consists of a list of divisors of 12. We see 1, 2, 3, 4, 6, 12. So this is what was considered in our theorem. And this is what we have started writing in the proof. Now let us look at again this statement that we have written here. Let D divides P minus 1. Xi D denote the number of integers K. K lies between 1 to P minus 1 that has order D. Now how many integers do have these order? So obviously because we are only counting, 1 has order 1, 3 has order 3 has 2 integers which have 3 order. For order 4 there are 2 integers. So we are only counting these numbers again. This is same as P minus 1. When we run over D P minus 1, now how do I have written this in the form of the summation? This expression. Let us look at this again. Summation D divides 12 Xi D. Xi D is, if D is equal to 1, those number which have order 1 plus those number which have order 2 plus those number which have order 3 plus those number which have order 4 plus those number which have order 6 and plus those number which have order 12. Order 1 has one number, order 2 has one number, that is 12. Order 3 has two numbers, 3 and 9. So there are two numbers. Order 4 has two numbers, 6 has two numbers and 12 has 4 numbers. When I am summing this quantity, I will get back to 12. So that is why this is same numbers. But now rather than counting into this form, what we are doing is we are counting according to their order. And also one more very important thing. Now looking at the last statement, once we see, we have started from P prime. We have considered P minus 1 divisor. Okay. So whenever D takes this value last order. So now again if we look at the stage, we have considered D as a divisor of prime. We wanted to look at congruent to 1 modulo P, a number A that can act as a primitive root. So this means here we should have phi P. And phi P, to search phi P, we have considered the list of the divisors. And in the divisor, that means this divisor have the order. So this may also treat it as order. So this means this is the smallest power that makes this whole congruence to be exist up. So whenever D has the last order, this is 12. This shows that these will become the primitive roots. These will become the primitive roots. So this is bound to happen. That ensures that whenever we say that there are integers order D modulo P, this has exactly phi D. This means whenever we talk about prime, we talk about some exactly phi D incongruent integer that act as the primitive root of the prime, of that particular prime. Now let's continue proving this theorem. So we have simply defined here, let D divides P minus 1 and xi D, and we have reached to equation number 1. Now from here, equation number 1 onwards, I am going to now take the use of the simple Mobius inversion formula. From 1, what we have considered is, we have P minus 1. This is equal to summation D divides P minus 1 xi D. And also we know that P minus 1 is same as summation of D divides P minus 1 phi D. This is same number. We have already done this result, that summation of phi of D, whenever D divides n, this comes out to be n. So that's the Gauss theorem. We have already proved that in my earlier video. You can check that this expression in the phi function. So this means this also hold. So from these two, so if I consider now 2, and this was our, this equation, this was 1. Okay. So from 1 and 2, we see xi D is equal to phi D. Now how to prove this? Because here it is summation sign. Now to prove this side, to prove the exactness of this expression, because if I only compare 1 and 2 equation, left hand side are same. So from left hand side same, what I am getting? I am getting D divides P minus 1 xi D is same as summation of D divides P minus 1 phi D. But it does not directly imply this case. Okay. It is possible that whenever I open, I have 1 plus 1 plus 4, or here I may have 2 plus 1 plus 3. So this situation will not occur. Rather, the corresponding quantities are going to be equal. So to prove this, let's consider now. Let D is the summation of C by D xi D. I am just considering this into another form of our Mobius function form. So here if I again compare, here Fn is summation of f of D, D divides n. So now what I am going to do is compare from here. Comparing. So when you compare from here, that means we are considering from here D as C. So read D as C. Here I have D, here I have C. Read N as your D. Okay. Then this expression, which I may write it as star, then star expression and double star expression are exactly same. Also, what is capital Fn? Capital Fn is replaced here by D. So in this I have Fn, and on this side I have small fd is replaced by xi c. From the Mobius inversion formula, what can I have? I have f of n. This is equal to summation D divides n mu D times f of n by D. This is the Mobius inversion formula. Apply the Mobius inversion formula here. When I apply Mobius inversion formula, what I am going to get? I am going to get xi D. This is equal to summation C by D mu C and D by C, because the left hand side is Fn is D. So I am going to write D by C. Now also I am also going to use that we know summation. Now also I know that summation D divides n phi D, this is n. So let's write this into this form and again apply Mobius inversion formula. So this is the same expression. Take Fn is equal to this quantity and small fd is equal to this quantity. So applying Mobius inversion formula, what do I have? I have here phi n. This is equal to summation mu D, D divides n and n by D. Now look at this expression and look at this expression. They are exactly same. They are exactly same except that C is replaced here by D and D is same as n. So in the expression now, in the expression delta and the double delta, they are exactly same because we are talking about the divisors of, here C is a divisor of D, here D is a divisor of n. Okay, so that ensures that xi D is same as phi d. So this implies xi d is same as phi d using delta and double delta. Now let us see this again in the example. So the proof was not difficult. What we have to do is, let's see again a quick glimpse of the proof. We wanted to prove that for every prime number d divides p minus 1, there are exactly phi d incongruent integers having order d modulo p. So we count another function phi d that has order d. Okay. So that means now we want to count all integers 1 to p minus 1. We want to count all integers 1 to p minus 1 that has order d. And write this p minus 1 numbers in the summation form. Now we just wanted to show that this summation form, which is the right hand side, is nothing but this is same as phi d. So we use now this expression which is given by equation number 2, which always hold because the star always hold. So now after comparing we see that not only summation but their correspondingly quantities are same. So not only the summation but the corresponding quantities are same. And to do that, we simply write now again our one equation in the form of this. And then we apply Mobius inversion formula. So here we have applied Mobius inversion formula twice. Once on xi function and once on phi function. And it shows that the both quantities are same. Now let's continue the same example one more time. And let's evaluate the phi expression towards that. So in the previous example, what I have considered here is, I have considered prime as 13. And for this, the choices of A can be 1, 2 up till 12. So from this, I see 1 has order 1, 12 has order 2. And then I may say 3 and 9 have order 3, 5 and 8 have order 4, 4 and 10 have order 6, and the remaining integers 2, 6, 7, 11, they have order 12. And hence we have written summation of d divides 12 xi d. And if I open this, xi 1 plus so on plus xi of 12, this quantity is 1 plus 1 plus 2 plus 2 plus 2 plus 4. That is equal to 12. And how did I have counted? I can count how many numbers do we have in this side. Okay. Now let us see the other way around, because we also wanted to calculate the xi d. So to calculate the xi d, what we have shown is xi d is always equal to phi d. This is what we have claimed. Let's look one by one. Xi of 1, because divisor is 1. So divisor is 1. This is same as phi 1. In this side, there is only one integer which have order 1, which is true. Phi 1 is 1. This is by definition. Phi n is the number of integers that are relatively prime with this n. Okay, number of integers that are relatively prime with n and strictly less than n is 1. When I take xi 2, xi 2 means number of integers that have order 2. How many integers we have order 2? Only 1. On this side, when I consider this as phi 2, phi 2 means only there is one integer which is relatively prime with this 2. This is also 1. Look at the next list of the divisor, phi 3. There are two integers which have order 3. So this means this is 2. I am looking it from here. And phi 3. By definition, there are two integers which are relatively prime with 3. 1 and 3 has GCD 1. 2 and 3 have GCD 1. So this means this number is 2. Then look at the next list, phi of 4. There are two integers again whose order is 4, and on this side phi 4 again this is 2, 1 and 3. Then we look at xi 6 and we look at phi 6. This is also 2, and there are two integers which have order 6. Xi of 12. This is the last divisor that I am looking up. Xi 12. There are 4 integers which have order 12. So this means this side is 4. And if I want to look phi 12. So we know by definition phi 12. This is nothing but it is phi of 12 square into 3. And when I apply the formula, This means it is 12 into 1 minus 1 by 2 into 1 minus 1 by 3. This comes out to be 4. So this is 4. So we can see here it is equal divisor by divisor. So if I look at the last stage, for all those integers, for all those possible a's, this is the list that comprises of a. For all those possible a's whose order is the last divisor, and always the last divisor is phi of that number itself, p minus 1 itself, because d divides p minus 1. So this means they will act as the primitive root. Of course, it does not reduce the calculation process. We do need to calculate all the congruences, and we do need to calculate the order calculation in the congruences classes. But what this tells us is that there exists a primitive root for every prime. So this is all about this theorem of the prime numbers. Next, we provide an alternative proof of this theorem using the Lagrange theorem. So here in the last case, I have utilized the mobius inversion formula, and here I am going to use the Lagrange theorems and hence its corollary. So I have added the proof of the Lagrange theorem in the description box, and also I have given the proof of the corollary. So let's start proving this using that Lagrange theorem. Now again in this case, let d divides p minus 1 and xi d in the same way. I am going to count. This denote the number of integers. This denotes the number of integers, not integers, count of integers, k such that 1 less than k less than or equal to p minus 1 that have order d modulo p. And of course, because each integer lies between 1 and p minus 1, because each integer between 1 and p minus 1 has order d, for some d divides p minus 1. So this point holds, as I have already explained this point in my previous proof also. Okay, till here it is okay, same. And also by Gauss theorem, we know that p minus 1 is same as summation of d divides p minus 1 xi d. Now 1 and 2, so these two ensures us, so 1 and 2, this implies because their left hand side is same, what we have is summation p minus 1 xi d. This is equal to summation d divides p minus 1 phi d. Now from here onwards, now we want to use the concept of the Lagrange theorem. So our aim is to show, xi d is equal to phi d. Now suppose if it is not there, okay, and we consider that xi d is less than or equal to phi d, okay, and we may also consider now here, note that xi d equal to phi d is not equal to 0. If they both are 0, then obviously we are not going to prove anything, because phi of 1 is also 1. So phi d is the count of integers which are relatively prime with d. So this count is not 0. And now we start our proof. Given an arbitrary divisor d, of p minus 1, there are only two possibilities. There are two possibilities. And what are the two possibilities? Either xi d is equal to 0. So this means there is no integers such that that is equal to 0. Okay. No integer which have the order d. And xi d is strictly greater than 0. Now if xi d is equal to 0, this implies, but phi d is not equal to 0, because phi d is the number of integers that are relatively prime with d. So there will be some numbers. In fact, minimum phi of 1 that we are talking about, it has the value 1. So this means xi d is always less than or equal to phi d. So this is what I'm going to get. In fact, strictly less than in this case. So suppose that on the other case, now suppose that xi d is greater than 0, so that if it is positive, that means there exists an integer a having order d. Integer a having order d, because this is what we have given in the definition of xi-d. Xi-d consists of the number of integers that have order d. And once you choose at least one number, we have at least one number such type, then the d integers, and that d integers I am going to consider the powers of this a square, a cube, because I know the maximum order is d. So this means all the smaller powers than d will not be giving me equations, that is, will not be giving me the congruent to 1 modulo d, because it is the order. So for none of the smaller power, I am going to get congruent to 1 modulo p. So these will be incongruent modulo p. Yeah, these will be incongruent modulo p. And each of them also satisfy the polynomial congruence. Each of them also satisfy polynomial congruence. Now because they satisfy polynomial congruence, so obviously I am talking about the Lagrange theorem. And what sort of polynomial congruence they satisfy? X to the power d minus 1 is congruent to 0 modulo p. And why would they be satisfying? Because I have said that the least power is t, only for d it is going to be congruent to 1. Let us see now. Because if I take any a to the power k and then I take raised to power d, this means this is congruent to a to the power d, and then we take to the power k, this is congruent to 1 modulo p. It will give me, for some values of k, it is possible to have, when I raise this power by d, it is possible to have that this is congruent to 1 modulo p. And this means now by the corollary of Lagrange theorem, which says that now we have something related to x raised to power d is congruent to 1 modulo p. So this means it has exactly d incongruent solution. So corollary of Lagrange theorem says that, let me name this as equation number star now, that there can be no other solutions of equation star. So only these d incongruent solution will exist, not any other. And this implies that any integer having order d modulo p must be congruent to a square up till a raised to power d in some order, because these were the least. So if I choose any higher power of this, they must be incongruent to this in some form. And how many are these? So this implies but only phi d of the just mentioned power. So that means the powers that I have mentioned here have order d. Because why will have the order d? Only for these we have already done to have the order. Say if a raised to power h has the order, then it has the order, so it must be divided by GCD of h and k. We have done this also in the earlier case. If the GCD is 1 only, then it becomes a same order power. So that is why, and to check the GCD of this, that means it has to be again phi d of the order. So this implies the only possibility is, so namely those AK for which the exponent k has the property that GCD of k and d is equal to 1, and hence this implies Whenever d is positive, this is same as phi of d. Whenever this is positive, this has to be equal to phi of d, and that proves our result. And in fact, this gives us a very nice corollary. So whenever d is p minus 1 for a particular prime, that means whenever d is the last divisor, that is p minus 1, this means that there are exactly phi of p incongruent primitive roots of p. Incongruent primitive roots of p. And we may in fact solve this one. So this becomes phi of p minus 1 incongruent primitive roots of p. So that talks about the existence of primitive roots in the primes.